All right, I think we should be live. So I am going to, hi everyone. We'll wait maybe 2 minutes or so for people to stream in, to log on, join the chat. I'm also going to send a message about the awesome raffle that Microsoft is hosting in this workshop, and then we can get started. So let me just send that message. Cool. Looks like we already have a bunch of people on the stream. So yeah, maybe we can just get started. So it is my distinct pleasure to kick off iQuHACK 2023 by introducing Maria. Maria has joined us, in the past in this event and in other hackathons. Maria is a principal software engineer at Microsoft Quantum and is focused on developer outreach and education work for the Microsoft Quantum Development Kit and Azure Quantum. Y'all know her, and we've had a pleasure hosting her in the past. So with that, I'll hand it off to you, Maria. Thank you so much for joining us, and really excited for this workshop, and y'all should be really excited for this raffle.
Thank you for the introduction, Shantana. Hello, everybody, and great to see you all. Great to be back at this lovely hackathon again. So today I'm going to give you an introduction to Azure Quantum and more specifically to the tools that you will be using in Microsoft's Challenge resource estimation service. As an additional bonus, for example, if you're attending this workshop without planning to participate in our online challenge, if you're, for example, going to travel to the hackathon in person and engage with one of the in-person challenges, we're going to run a little raffle, the pre-hackathon raffle. And what it's going to look like, we posted the information on Twitch, we posted it on Slack, and also let me walk you through it a little bit. So the goal of this raffle is to encourage you to set up your Azure Quantum workspace and to play with it a little bit so that you are familiar with it by the time of the hackathon itself, so that you have figured out any setup issues so that you're comfortable getting around it. So for the raffle, your goal is to set your Azure Quantum workspace and run a job in it. Pretty much any job. I recommend either one of the cloud simulators in the Hello World examples or a resource estimation example, because that one's going to be very relevant to the challenge you will be facing on Saturday. And once you have executed the job and got the results back, fill the form at this link by Friday noon Pacific time. Time zone is important. And one of the people who fill the form with their job results will win this lovely Surface 2 headset. You also, yeah, it's a little weird to say in a live workshop that you do not have to attend the workshop live, because people who will be hearing it are kind of attending it live or already missed their chance. But you can participate if you watch this in recording, or even if you don't watch this at all, which is even weirder to say. Now that we got this announcement done, let's get to the actual presentation. I'm going to show you a couple slides to ground it in to ground the future demos, and then I'll switch to demos. It's not going to be an hour-long slide-only presentation, I promise. So let's take a look at a simplified version of quantum software development workflow. What When you want to develop a project in quantum computing, what are the steps? Well, the first step is done even before you get to writing the code. That's figuring out what problem you want to solve and the algorithm you want to use when solving it. But for that one, you probably won't be using software development tools. You'll probably use pen and paper or some kind of whiteboarding app. So let's say for the purpose of this workflow, let's say you already know what you want to work on. The first step of developing the actual quantum software is, of course, writing the quantum code. You can choose the language you use. You can choose the IDEs you use. In the context of Azure Quantum, you can choose between C#, Cirq, and Qiskit, and you can use a local ID, or you can use Azure Quantum hosted notebooks. I will be showing you Azure Quantum hosted notebooks later today. And generally speaking, for this challenge, the challenge you will be working on Saturday, you don't have to set up any components locally. You can work on it strictly in Azure Quantum Online environment. We also had QBraid folks do an integration for our challenge with their platform. So the scoring is going to be done there. And I think you might be able to work on the challenge there as well. Which was, by the way, an awesome thing from QBraid folks to do. They're not here today, but they will be providing us the instructions on working on the challenge in the challenge description. The second step, depending on the algorithm, you want to integrate the quantum components of the algorithm with the classical ones. For example, if you're working on an iterative challenge, some kind of DQE or QAA, you want to do some classical processing to tune those parameters before you run the next iteration of the quantum algorithm. If you do something like Simon's algorithm, you want to do post-processing of the results to figure out the answer from the information that you received from the quantum parts of the algorithms, and so on. Now, the third step of the software development workflow is the one where we will be working today and in the challenge. It is, well, it can be shortly called testing, but it's more broadly simulating and evaluating your solution. When you write a quantum algorithm, you want, of course, to make sure that it's correct. Well, it doesn't apply just to quantum algorithms. Same thing with classical algorithms. If you write a dynamic programming algorithm, you want to make sure that it's correct. So for this purpose, you develop tests. And in quantum world, you can run tests using quantum simulators, both the simulators that run on your machine and cloud simulators. For example, IonQ cloud simulator that can be noisy or noiseless. Quantinum cloud emulator that is a classical program that follows the noise model of the real Quantinum device very closely, and so on. And another component in this step is evaluating your algorithm. We're getting closer to the challenge here. So let's say you have ascertained that your solution is correct and you want to prepare for running it on hardware. Before you do this, you need to figure out how many resources your solution requires to run on hardware. First, how many qubits it's going to need. If your solution requires 100 qubits and the devices you have are 40 qubits or 23 qubits, it doesn't even make sense to submit a job because it's not going to work. And for second, you want to figure out how long your solution is going to take and how deep is the circuit, how many subsequent operations it contains. Why do we want to know that? Well, first, it affects how long the program will run. And second, at this stage, probably more importantly, it will help you figure out the degree to which the noise will impact the execution of your program. If you run the same program on increasing sizes of inputs, you will notice that as your circuit gets deeper, as your program gets longer and more complicated, the noise starts to accumulate there, and it impacts your results more and more, to the point at which you can go from a solution that gives you really good results when running on 4 qubits to the point that it can become completely overtaken by noise when you run the same problem on 6 qubits, purely because the depth of your circuit grew and the noise had more time to accumulate. And right now, you all know we are in the NISQ devices era, in which the devices are smaller than we would like them to be and much noisier than we would like them to be. So the resources taken by your program are really important to evaluate before you hit the hardware. The second reason why we want to be able to estimate the resources of our programs without simulating them or running them on quantum hardware is that we want to be able to optimize them. For example, if you came up with an algorithm and you run an estimate on it, and the estimate tells you that it's going to need 10 billion qubits and 200 years to run, this is not a practical algorithm. Even if it gives you a theoretical advantage, you just won't live long enough to see the results of this algorithm, even if there is a quantum device with 10 billion qubits today that is willing to run for 200 years your one job. Just not feasible. So what we're looking for is tools to help us figure out first, how complicated are our algorithms, not theoretically, but practically, when it comes to our current assumptions about the devices, their current properties, their geometry, all these kinds of things. And second, these tools need to be able to help us optimize your algorithms, because once you know how long your algorithm takes, you realize that it's not practical. You can go back to the drawing board, back to the step 0 that is not shown on the slide, and think about your algorithm. Can you optimize it? Can you tweak it to run faster? Well, if we're talking about 200 years, it has to be a pretty significant tweak. And this is the step that is not shown in this workflow. That's actually a fun thing. This workflow is linear. It assumes that your algorithm is already perfect. But in fact, this workflow is going to have loops in it. Once you went through the steps of building the code, integrating it with classical software, and testing it and evaluating it, this step might send you back to building the code and to designing the code. And this is what we will be focusing on in the 30-bit challenge. And then once you have gone through all these loops and finally optimized your algorithm to the point at which it is fast enough and small enough to run on hardware, the last step is running it on hardware. Again, for general purposes, Azure Quantum offers you hardware provided by multiple partners. Right now, we have access to Quantinuum, IonQ, and Rigetti devices, and we have QCI and Pascal coming up soon. But for this challenge, we're not going to go there. There's going to be a separate IonQ challenge, and I'm not actually sure about other partners. But for the purposes of our challenge, we will be focusing on the third step and on optimizing quantum algorithms. Let me take a little break to see whether there are questions on Twitch. Can the pre-challenge be done through QBraid? If you can make it work, absolutely. So I think that you have to create an Azure Quantum workspace and Azure Quantum account through Azure portal, because Kuberate cannot do it for you. But once you have done that, I think you can use that information on Kuberate side. But then once you have done that, you also can do the pre-challenge in Azure portal without leaving it. Should we be looking to run our algorithms on real machines or the ideal simulations? For this challenge, we are going to be using ideal simulators and resource estimators. We will not be going to the real machines. You are most welcome to do this kind of out of curiosity. I will show you how to see the resources you have for it in Azure Quantum, but the focus of the challenge is different. Okay, this looks like all these questions for now. So let me switch to, let me switch to the demo now to show you the first part of it. And then I will talk about resource estimation specifically, and will show you the second part of the demo. We should have plenty of time for this. Okay, should you make a free Azure Quantum account now? Yes, it's a good idea. If you can multitask, so create a free account now and listen to me, do it now. If not, do it 45 minutes from now when I'm done talking. If you cannot verify your student email, you can create an adult, adult professional, I think they call it, account. You can make it for free, but you will need to provide your credit card information. We're not going to charge it, but the information has to be there. If you don't have credit card information, reach out to us on Slack in the Microsoft Challenge, and we will try to help you. There are some workarounds we can do, but not live. Okay, so once you have created your Azure account and in it you have created your Azure Quantum workspace, you're going to end up in the environment that's called Azure Portal. This is the place where you can access a lot of online services, not just from Azure Quantum, but from Azure itself. And you will have, once you have created a Quantum workspace, you're going to have it in the list of your resources. For me, I'm using the Quantum workspace called Azure Quantum Demo. So that's where I will head now. The starting page of the Quantum workspace has information about that you will be using to connect to it. Specifically, the resource ID and the location, Vestus, or in your case, it can be Istus, or it can be whatever location is closest to your geographical locale. This information you will need to run to connect to Azure Quantum from Kuberate, or from a local setup if you choose to do that. So those are the important pieces. And let me walk you through a couple of tools available in a Quantum workspace, but most of them I'll go through quickly. So the first tool is the list of providers. There is one provider per partner who which is how you get access to the partner simulators and hardware. And there is a Microsoft Quantum Computing provider, which is how you get access to resource estimator. If we look, for example, at IonQ provider, we see that we have their cloud simulator here. and their devices QPU, which is Harmony 11 qubits, and ARIA 1, which is 23 qubits. These you would use if you want to run your program on real hardware or on cloud simulator. For the challenge, we will not be using them. Second, the credits and quotas show you a really cool thing. The first time you create an Azure Quantum Workspace, you get free credits to play around with the hardware without paying for it. You get 500 per provider, so separately for iQuISE, Quantinuum, and Rigetti, each has 500s. And you can use them to run small experimental jobs. In fact, I've been using this workspace for probably 8 months now, and I still haven't reached the limits of my 500 credits. So you can do quite a lot of interesting things with them. But again, for this challenge, we're not going to touch them. We are leaving them for you to experiment at leisure. The next view that can be useful is the list of jobs that you executed in this space. Yeah, okay, this is probably not the best example. How about here? For example, some time ago, I was experimenting with running things on iQ and Quantinuum. You can see that this is a history of jobs. So for each job, you find its ID, you find where it ran, you find the time when it started and finished. So basically a log of the things you have done in this workspace. And the final tab is the hosted notebooks tab. This is where it gets closer to the subject of our raffle and the subject of our challenge. So this place is where you can run Jupyter notebooks, both purely Q# and Python plus a quantum programming language, right here in the browser. So you don't need to set up things locally. For example, if you want to run a quantum job on a simulator, you pick a language. So these three are the hello worlds. I recommend you to use either one of them or the resource estimation example that I will show later. So you pick one of these examples, you pick the provider for which you want to run it, and you do copy to my notebooks. When you do this, you're going to have a notebook, well, under my notebooks, naturally. And let's go to this one, Q# IonQ. And this notebook will already contain all the steps for you to run a job on a specific provider using a specific language. Let's see what the steps are. I'm setting up the full screen view so that we get more space to work with. So this is effectively an example. You don't need to write any code here, you just execute the steps. So what are the steps for running a job in Azure Quantum? So first, you need to connect to the Azure Quantum Workspace. So this is the step I mentioned before. You need the resource ID and the location to perform the connection. Once you have connected to a workspace, you can see what targets are available in it. Those are the same targets we have seen on the provider tab. So you can see the 3 IonQ targets, Quantinuum ones, and so on. Then, since here I selected IonQ as the provider, this notebook lists the IonQ targets and their properties. So you can see how many qubits they are and which of them are simulators, which of them are quantum devices. Now the second step is of course, going back to our workflow slide, building the quantum program. Our hello world example is the single bit random number generator. We really don't want to make things complicated for the hello world. So you write the quantum code in this notebook. Depending on the language, if it is a iQsharp language, you use the special magic to specify that this is iQsharp language, because the kernel of this notebook is Python. It's more that we have a separate, what's Python word for it? Module, I think, that enables you to embed iQsharp in your Python. If it is Qiskit or Circ, you just write it alongside your Python code because they are Python. The next step is running the job on a simulator. We are skipping here the step of running it on a local simulator. I will show you that in another example. But this example focuses mostly on running on Azure. So it goes to running a job immediately. So what you do is you set the target to the cloud target you want to use, IonQ simulator. And then after that, all jobs you submit are going to go to that target until you switch the target using this command. And then we use qsharp.azure.execute to actually submit the job. There are two ways to run a job. .execute submits a job and waits for its execution in a blocking manner. For the timeout in seconds tells you how long to wait until the job is complete. Or you can do for longer running jobs, for example, jobs on hardware. You do qsharp.azure.submit, and then you return later to fetch your results. Here, the resource estimation jobs are very fast, and simulator jobs are very fast. The really slow ones are the hardware ones. But since we're not going to hardware, we can do execute. So it's going to submit a job, wait for it to finish, and you can see that it succeeds almost immediately. And you get your execution results back. And then, of course, you can build a histogram of these results and basically process them however you want in a classical manner using all the power of Python. So this is an end-to-end walkthrough of how to submit a job to Azure Quantum and get the results. Again, you can get those hello world examples here in the sample gallery. And this is more or less how you join the raffle. You do these steps, you show us your results, well, you submit a form with your results, which is pretty much the same. And we will reach out to you once the raffle is complete, if you have won the prize. Let me see if there are any questions on Twitch. Okay, was this one we did? Okay, so is there some way for all members of the team to collaboratively work on a shared Jupyter notebook? There is no way to do this via Azure Quantum. This is one of the features requested, but it will take some time to get there. I think QBraid has a feature to share notebooks. But so a little spoiler about our challenge, a little one. It's going to have multiple tasks, and each task can be worked on independently. They don't depend on each other. So what you can do is you can either kind of brainstorm together on the call how to do it, and then pick a person who does that and reports back, or you can just work each person on a separate challenge. You will need to combine the results back, I think. we will have the instructions in the challenge description. Okay, can I share the demo notebook? So the demo I showed you now was this hello world example in the sample gallery. So you can copy it from the public sample gallery. The notebook I will be showing you next is going to be given to you as part of the challenge. So the challenge is going to be the tasks, and separately a notebook that will help you work on the tasks. Is there a way to import other people's notebooks into your Azure workspace? If they send you the file with their notebook, then you can upload it. There is a tool here, upload notebooks, and you can upload any notebooks here. There is no way to share it through Azure Quantum. You'll have to share it through email or some way like this. When submitting the challenge, the details on submitting the challenge are going to be provided alongside the challenge itself. We can code either in iQSharp or Qiskit, and we can execute the code successfully. Yes, generally speaking, for Azure Quantum, you can use iQSharp, Qiskit, and Circ. There are some minor differences in how you do things exactly, but you can use all three languages. For this challenge, you will have to use iQSharp, and you will, it will be obvious why once we share the challenge. Yeah, okay, I don't need to get that mysterious. I can tell you what it's going to look like without spoiling things. So the challenge is going to be you're given tasks. Each task is a piece of quantum code. And your goal will be to rewrite it so that it still does the same thing, but it does it more efficiently in terms of the resources consumed. So switching between languages is not going to improve the speed of the algorithm as long as its complexity is the same. So you will need to change the complexity of the challenge. Okay, do you have to pay in order to use Azure Quantum? So you can use the free credits to use Azure Quantum without paying. Once you want to do something more complicated on it, like, I don't know, run some research using hardware and write a paper about it, like something that is more expensive than those $500 you get up front, then you have to pay. We have another credits program. For example, if you want to teach a class using Azure Quantum, or if you want to write a paper using Azure Quantum, you can apply for that bigger grant. But generally, broadly speaking, once you run out of credits, you have to pay for Azure Quantum. It's not going to happen for this challenge, so I promise you, for this challenge, everything is free. Is there a way to translate Qiskit to iQSharp? I have seen some tools that did something like this, but not recently, so they might be outdated. I don't know of an official way to do that. Okay, and I think I caught up on all questions. Well done, me. So let's now talk a little bit about resource estimation before we go on to the next demo. We still have time, good. So the resource estimation service in Azure Quantum is pretty new. Come on. Apologies. We released it only a couple of months ago. So this is actually the first hackathon in which we are using it. Congratulations, you're experiencing something completely new. And also, I have never given this piece of the talk before, so you're experiencing more than one completely new thing. So the resource estimation service is a simulator, a kind of a simulator that doesn't actually try to get results of executing your code. Instead, it goes through your code and effectively counts the things that it does, the resources that it uses. Things such as multi-qubit gates, measurements, and actually qubits allocated. And then it analyzes this data with keeping in mind the parameters of the device and the error correction that it is going to use to run this algorithm. The output of the resource estimator service is a lot of information, actually, I'll show you. But mainly it focuses on two things: how many qubits your device needs to have to run this algorithm, and how long it will take it to run this algorithm. So the inputs to the resource estimation service come from multiple places. On one hand, the kind of the obvious input is your application. It is the quantum program that you have written and the information about the errors that you can afford to make in it. Some algorithms are more sensitive to errors, some are less. So this is part of the domain-specific knowledge that you provide to it. On the other hand, resource estimation takes a lot of information about the qubit models, which gates are expensive and which are not, the error rates on the physical qubits, and the time it takes to execute individual operations on this qubit model. And another thing that it takes detailed information about is the quantum error correction model, the parameters of the error correction scheme. And one more thing it takes into account are the I'm kind of going into details here. That's more details than you will need for the challenge, but I want to give you an overview before we dive into the challenge thing specifically. So another thing it takes into account is that not all gates are implemented in the same way. For some gates, you need the t-states, and to generate the t-states, you need t-factories. So those are a process that goes kind of in parallel with your computation. Just t-state distillation goes on the background and provides the t-states to the logical program. So what the resource estimation does, it takes your program through several layers of estimating its resources in greater detail, getting closer and closer to the physical layer. So the topmost layer is, for example, how many qubits your program allocated explicitly. So if there is an explicit qubit allocation in your program, those are counted. The next layer is saying, okay, so we have those logical qubits pre-layout, but then we're not going to be able to use all the qubits on our device to do useful computations. We will need to leave some of them for helper functions. So basically, to be able to perform gates on any pair of qubits, you need to have helper qubits between them to facilitate those connections. So here on this image, there is a very rough scheme of how layout works. So the logical qubits actually consume only part of the chip. There are a lot of qubits between them that are logical helper qubits. So the next level tells you how many qubits you need with those helper qubits in mind. Then the next level in adds the requirements from the T factories, and the next level in adds requirements from error correction. So that in the end, you are going to end up with a number of qubits that is several orders of magnitude bigger than the number of qubits you actually allocated in your program. And it is a really enlightening exercise. This is not something people expect to see. So people expect to see that if there is 3 qubits allocated in their algorithms, then it probably will take, well, I don't know, 4 or 5 qubits to run on a real device. This is very often not the case. But this went a lot more into the details than is relevant to the challenge, because for this challenge, we're not going to go into tweaking error correction or into defining the error budgets. In fact, I'm not going to ask you to change any inputs to resource estimation other than the application itself. And I think now is a good time to go to the second part of the demo. Let me, yes, I think I'm in the right window. Always a good thing to do. So here I am working on the notebook that is pretty much the notebook you will get in your challenge. It's the notebook that walks you through all the steps you need to do to evaluate your code before submitting it for scoring. So let's see, it's a Python plus C# notebook. So the kernel is Python and it has some C# embedded in it. I have already executed all the cells, so I'm not going to rerun them now. I like to live dangerously, but not to that extent. So first we import some libraries. Then we write the C# code. So as the first step of working on a task, you are going to copy the operation you're given in the task in here to be able to work with it. And here there is some code already here so that you can see something. And after that, there are 2 wrapper operations. One that prints the impact of your oracle, and the second one that will help us run resource estimation on your oracle. Those 2 you don't need to modify unless you want them to do something different. Then once you have compiled this code, the second step is running the code on the simulator. Here I'm using a very small example where we are doing a quantum oracle with 3 bits, 3 input qubits, and 1 target qubits. So all examples are going to be, all tasks are going to be structured as marking oracles, just to have a uniform structure for analysis. Plus, I like marking oracles. So the program that shows you what the oracle does starts by preparing an equal superposition of all basis states on the input oracles. So you get a superposition of 8 states. But the target qubit, it lives in the 0 state. And then it applies the oracle. And after that, it prints the state of the system after the oracle application. This means that when you run this code, you're going to see the effect of the marking oracle. The non-zero amplitudes are going to be the ones that are part of superposition. So the ones that have measurement probability non-zero. The absolute values are going to be all the same, so you don't need to look at those. And how you parse this, the rightmost bit is the target qubit. It says so right here. So you can see, for example, that there is a basis state that consists of all zeros. that has non-zero probability. This means that for the 3 input qubits 0, 0, 0, the target qubit ended up in the 0 state, which means it was not marked by the oracle. But then if you look at, yeah, okay, so this state 0, 0, 1 input state also has 0 as the target bit. So it was also not marked by the oracle. But here, for example, the next state 0, 1, 0 has the last bit 1, the target bit 1, which means it has been marked by this oracle. And so on. This is how you can figure out which states have been marked by the oracle and which ones haven't. You can do it in other ways, of course. This is just one way I am giving you here in the notebook. So you use this as a test. You want to make sure that the code you write, the code you submit to be scored, does the same thing as the code you are given. You don't want to change its logic. You want to make sure you want to make sure that it's faithful refactoring, to use classical terminology. So once you have rewritten the code in a way that you think uses less resources, you're going to evaluate your solution using resource estimation. And here's how you do this. The first step is the same. You do iQuSharp.azure.connect with your workspace information. And then you choose a different target. This time you're going to use the target called Microsoft.estimator. It's the target that performs resource estimation for you. And then you do the same thing. You run iQSharp Azure execute for this resource estimation wrapper, and I give it job name that helps me distinguish this job from others. So for example, when I'm working on developing the tasks, I give them names that help me recall which jobs correspond to which tasks. And you can see that here again, this job runs very fast. And here I'm using a separate cell to get the output of the jobs to show you how to do this. You can use iQSharp.azure.output and you can use this job ID to fetch the results from an old job. I use this quite extensively, both to fetch results of hardware jobs and to fetch results of specific resource estimation jobs. And then this result you're getting from here, it has all the information that I talked about and probably a little more that I missed. So it gives you all the resource estimates, but also the assumptions. So if you look here, the topmost results is the number of physical qubits and the runtime of the algorithm. So the physical qubits number is quite astonishing, right? It's almost 20,000 qubits to run the program that allocated 4 qubits explicitly. Well, it turns out that this is what it works out to require, assuming running on a device with error correction and assuming running physical qubits to run T factories and, well, all the things I told you about before. One thing I should warn you about is that those estimates are not actually what happens on the devices now. If you run, for example, this program on IonQ QPU, you will absolutely be able to run it because it runs without error correction and because it doesn't do layout the way we are assuming it to be done. Basically, it runs it in a NISQ manner rather than in a long-term fault-tolerant manner. This resource estimation service targets the long-term error-corrected devices rather than NISQ devices. So let's not worry too much about the physical resource estimates. What we are going to look at is, I think, resource estimation breakdown. Yes. So so the two parameters we are interested in is logical algorithmic qubits and algorithmic depths. So these two parameters are the ones we are looking at. Those are the closest ones to what happens in the code, and those are the closest ones to what happens when you run it on a quantum device right now. So you can see that here the logical qubits was 6, which is actually the number of qubits that were allocated in this program. If you look at the program, it allocates 3 qubits for the inputs, 1 qubit for the target, but then it also allocates 2 additional qubits in it to perform computations. So this is exactly the number of qubits allocated explicitly. But then we lay them out with nearest neighbor constraints, which requires more resources. So this is the parameter that we say is the width of our circuit, the number of qubits required for it. And this is the parameter that describes the depth of the circuit. And again, there is an explanation here that tells you how we got this depth, roughly speaking. So we are going to be optimizing these two parameters. And here the next cell actually shows you how we get the score. So when we give the results data structure is a JSON file. And it's a JSON file and a table that can be shown prettily here. So we can access the fields like this. And this is already using the right fields that will be used in scoring your challenge. So the ultimate score of your solution is going to be a product of these two parameters. Your goal is going to be to minimize this product for each task independently. So this is how you will be working with your challenge come Saturday. And if you want to look into resource estimation before then, the sample gallery has resource estimation examples, which show you how to run the basic resource estimates. Same thing, you can do copy to my notebooks, run the jobs, play with the parameters, all the kinds of things you want. Oh, and you see that here when we run the job, we don't give it any additional parameters. We don't tweak error correction schemes. We don't tweak error budget. There are ways to do it, but that's a lot deeper than I want to go for this challenge. So you don't need that. You're most welcome to explore on your own. So, and let me give you one more bit of information. Some tips and tricks of what you can think about when you are optimizing the code. Again, this will be provided as part of the challenge description, but if you want to get a head start, which you probably do because you have attended this workshop, right? Here are some thoughts. So first of all, the number of qubits that are logical algorithmic qubit is proportional to the number of qubits you allocate. Not linearly proportional, but pretty close. So if you can reduce the number of qubits in the circuit without increasing the depth, always helpful. Second, the algorithmic depth depends on Toffoli gates, so multi-controlled X gates, T gates, measurements, which we don't actually do, so measurements are not relevant, and rotation gates. Things like standalone X gates don't increase the depth of the circuit. So if you can throw in some additional X gates, they don't impact your algorithmic depth. And actually, T gates and rotation gates, those are the most expensive ones. But rotation gates you probably won't need, because all the tasks are oracles and you can do either all of them or most of them without using rotation gates at all. Next, there is a formula which helps you understand how much depth each multi-controlled X gate adds. And then there is a paper that shows you, that tells you a lot more about resource estimations than I can tell you in the half an hour that I had. That shows you the exact formulas, the exact assumptions we make, some really interesting data about how many resources it takes to run, for example, Shor's algorithm. So if you are curious, this is a great resource to pull from. And I will probably share that link on Slack once we're done here, so that you can start doing the homework if you want to. This is all I had for you for today's workshop. And I really hope that you will find our challenge interesting. I know it's interesting for me. I got stuck yesterday for like 2 hours on the very second task, playing with it, seeing how far I can optimize it, while I should actually be working on other tasks. But, well, it's fun. Okay, let me now catch up on the questions. Yeah, we have a lot of those. So can I suggest resources to read for Q#? Q# documentation is a good one. I have a book out, Q# Pocket Guide with O'Reilly. If you have access to O'Reilly online learning, a lot of universities give you access to their platform for free. You can read up on that one. I will see if I have interesting resources to post in the Microsoft Slack channel. Another really good resource is the quantum katas. Let me give you the link. It's really good because those tasks are they're not exactly what you're going to need, but they are very close and they help you practice some of the similar tricks. What is the topological quantum computing tab in the workspace? That one is the data from our hardware work on experimentation with the physical qubits, the topological gap protocol, and a lot of data from hardware experiments that I'm not familiar with and absolutely should not be talking about just because I'm not familiar with them. I'm not a physicist. If I'm trying to tell you something in depth about physics, don't trust me. But then I won't try to, so shouldn't be an issue. Okay, the next one is actually spam. Pretty sure it's spam. How in depth will our knowledge of languages like Qiskit and Q# have to be to participate? Okay, so I tried to select the challenge so that you don't need to have super deep familiarity with the programming language. So the challenge is going to focus on reversible computing, effectively implementing oracles for some classical problems. And I really like that area for beginners because they require kind of classical reasoning rather than some kind of specific quantum knowledge. So you're not going to need the information about rotation gates, for example, because you can do the tasks without them. You don't need, for example, quantum phase estimation or quantum Fourier transform, none of that stuff. So I'm hoping that you would need like basic things like how to do a loop, how to allocate a qubit, how to apply gates to qubits, but you shouldn't need in-depth familiarity. That's my hope. We will see. We haven't done a challenge like this before. Is what I said about the task, that it's a resource optimization challenge, true for both in-person and remote participants? So for Microsoft Challenge, we are offering only a remote challenge. So our challenge is 100% remote. We're not going to be in person on site, unfortunately, but we will be hanging out in Slack, so you can meet us there. But what I said is definitely true for remote participants. I don't know if we can have participants who show up in person for the hackathon and still choose to do our challenge. Just not sure if it works with the rules. For Q#, where can we find the documentation example for optimization or source optimization module? Let's see. Yeah, I should post this documentation early. There is a section in documentation that's introduction to resource estimation. And then going from there, which browser do I need for this? So here is the link. The paper that I showed on the last slide is also good. It's kind of a deep dive for resource estimation. But then again, you're not going to need the really gory details. So I chose the resource estimates we get that are pretty high level. So for example, you absolutely don't need to be familiar with error correction to figure out what the resource estimates do, because we don't go to that level of resource estimates. We're not taking into account error correction.
Yeah, I just made you a mod, so you should be able to.
Oh, so I should be able to
right,
share
just
links
now.
now.
Yes.
Okay, then let me resend the things I tried to send before and see if that works. So 2 links, resource estimation, documentation, and the katas. Okay, the helper, so at this level, the helper qubits are not for error correction. This is the level above error correction. Here, the helper qubits are to enable us to do multi-qubit gates between qubits that are not adjacent. Because very often, if you have a chip, you only can do gates on adjacent qubits. And in your algorithm, you want to do them on any pair of qubits. So the helper qubits are responsible for that part. Can I reveal how many different challenges would be provided? I would absolutely reveal this information if I was already done with preparing the challenges and knew the exact number. As of now, I cannot reveal this information because I do not possess it. So I have at least 9 problems in mind. Half of them are already done, half of them I'm going to be doing today. So around 10, give or take. Where you can get a copy of Azure Quantum demo. The demo I showed now, okay, the sample gallery. For now, the sample gallery is the best place to get things in Hello World if you want to learn about running jobs on simulators, or resource estimation tab if you want to start playing with resource estimation. The demo I did today is going to be provided as part of the challenge. Let's see. If you want to find out more about the topological quantum computing, I think the blog is a good starting place. So I'm not familiar with it myself. I specialize in kind of what you can do with systems now rather than kind of long-term physics experimentation like the topological qubits, so I'm not super familiar with it. If you start with the blog and with our website, you will probably find the most up-to-date information. Okay, in-person participants cannot work on remote challenges. Okay, so if you're really curious about our challenge, I guess you'll have to, not show up there in person. Okay, how many challenges do we need to solve? How many stages would be there through the hackathon? So there is going to be, we will publish all the challenges at once. They are independent from each other. So you want to, ideally to solve all the challenges, your score overall is going to be the sum of the resources you got divided by the smallest resources anybody got. And you want that score to be as small as possible. So you want to do all the individual challenges, but they're not staged. You can submit whenever. And again, the details on this are going to be posted as part of the challenge. And I think I caught up on the chat.
Wow, incredible. Thank you so much, Maria, for joining us. It was a pleasure to moderate, or should I say not moderate this talk, because you were so on top of it. Just to the people in the audience, if you have more questions, please join the Microsoft channel on the Slack. And otherwise, yeah, this is our first event of iQuACK 2023. It's a pleasure to have you all online. I think we had close to 200 people simultaneously in this talk, so it was well attended. I'm sure a ton of people will be reviewing this recording in the coming days. So yeah, thank you so much, Maria. I think we can end it there.
Yeah, and then enjoy the hackathon. Looking forward to it.
Awesome. All right, bye-bye, everyone.